In this module 4, we will start with the definition of analytic function, the definition of ordinary and singular points of the differential equation. Given a second order differential equation, how to find the ordinary points and the singular points, how to classify them. In module 3, we have seen the solution of the second order differential equation by power series method about the ordinary point only. What difficulty we will be facing if we find the solution about the singular points and how to overcome it. These are the things which we will learn in this module. We start this module with the definition of analytic function. A function f(x) defined on an interval containing the point x equal to 0 is called analytic at x0 if its Taylor series given by summation n equal to 0 to infinity nth derivative of f at the point x0 divided by n factorial into x minus x0 exists and converges to f(x) for all x in the interval of convergence of 1. Therefore, sin x, cos x, e to the power x, all polynomial functions, they are all analytic everywhere. However, the rational function given by 3x plus 2 divided by x minus 7 into x plus 3 is analytic everywhere except at the point x equal to 7 and x equal to minus 3. Please note that at the point x equal to 7 and x equal to minus 3, this function becomes undefined, and hence this implies that a rational function is analytic except at those values of x where its denominator is 0. Next, we define what is a singular point and what is an ordinary point of a second order differential equation. A point x equal to x0 is called an ordinary point of the equation x double dash t plus pt into x dash t plus qt into xt equal to 0 if both the functions pt and qt are analytic at the point t equal to t0. If the point t0 is not an ordinary point of the differential equation 3, then it is called a singular point of 3. There are two kinds of singular points, namely regular and irregular. A singular point t0 of 3 is called regular if both the functions t minus t0 pt and t minus t0 square qt are analytic at t equal to t0. If not, it is called a irregular singular point. Let us take up some examples. In this example, we have to show that x equal to 0 is an ordinary point of the differential equation t square minus 4 x double dash t plus t x dash t minus x t equal to 0, but t equal to 1 is a regular singular point. The given differential equation, we rewrite it in the form x double dash t plus t by t square minus 4 x dash t minus x t divided by t square minus 4 equal to 0, and this we get by dividing the whole differential equation by t square minus 4. Next, we rewrite it in the form x double dash t plus t by t plus 2 into t minus 2 x dash t minus x t divided by t plus 2 into t minus 2 equal to 0, where we factorize t square minus 4 to get t plus 2 into t minus 2. If we compare the differential equation 5 with the general differential equation, then we will see that our pt is equal to t divided by t plus 2 into t minus 2 and our qt is equal to minus 1 by t plus 2 into t minus 2. Since both Pt and Qt are analytic at t equal to 0, therefore, t equal to 0 is an ordinary point of the given differential equation 4. Next we check about the singular point. We see both Pt and Qt are not defined at t equal to 2, and hence they are not analytic at t equal to 2, and therefore, t equal to 2 is a singular point. Please note, if we put t equal to 2 in Pt and Qt, we will get both the functions to be undefined, and hence they are not analytic at t equal to 2, and therefore, we conclude that t equal to 2 is a singular point. Also, we calculate t minus 2 multiplied by Pt, which is equal to t by t plus 2, and t minus 2 whole square Qt is equal to t minus 2 divided by t plus 2, given by expression 7. Now, if we put t equal to 2 in these two expressions at the denominator, they are not undefined, and hence they are both analytic at t equal to 2, and hence we conclude that t equal to 2 is a regular singular point. In our second example, we have to show that x equal to 0 and x equal to minus 1 both are the singular points of the differential equation t square into t plus 1 whole square x double dash t plus t square minus 1 x dash t plus 2 x t equal to 0, and then we have to classify the singular points. We divide the given differential equation by t square into t plus 1 whole square, and we will get expression 8, which is x double dash t plus t square minus 1 divided by t square into t plus 1 whole square x dash t plus 2 x t divided by t square into t plus 1 whole square equal to 0. If we compare equation 8 with the general equation, we will get that Pt is equal to t square minus 1 divided by t square into t plus 1 whole square, and Qt equal to 2 divided by t square into t plus 1 whole square, given by equation 9. Please note that this both Pt and Qt are undefined at t equal to 0 and t equal to minus 1. That is, if I put t equal to 0 and t equal to minus 1 in Pt and Qt, both the functions are undefined, and hence we conclude that they are not analytic at these points, and therefore, t equal to 0 and t equal to minus 1 are both singular points. Next, we have to see whether they are the regular singular points or irregular singular points. To do that, we will calculate t minus t 0 Pt and t minus t 0 whole square Qt. And if you do that, you will be getting, after some simplification, t minus t 0 Pt is equal to t square minus 1 divided by t into t plus 1 whole square, and t minus 0 whole square Qt is equal to t square minus 1 divided by t plus 1 whole square, given by equation 10. From 10, it is clear that t Pt is not analytic at t equal to 0, because if you put t equal to 0 in this particular expression, this becomes undefined, and hence t equal to 0 is an irregular singular point. We again check t plus 1 into Pt and t plus 1 whole square into Qt. If you simplify that, you will be getting t plus 1 into Pt is equal to t minus 1 divided by t square, and t plus 1 whole square Qt is equal to t square minus 1 divided by t square. From these two expressions given in 11, it is clearly seen that both t plus 1 Pt and t plus 1 whole square Qt are analytic at t equal to -1, because if you put t equal to -1 in the denominator of these two expressions, they are still defined, and therefore, we conclude that t equal to -1 is a regular singular point. We have just learned how to find the ordinary and singular points of a second order differential equation. In module 3, we have learned how to find the solution, the power series solution of the second order differential equation about the ordinary points. What will happen if you take the solution near the singular points? What are the difficulties you will be facing and how we will be overcoming them? This is what we are going to learn now. We consider the differential equation pt d2x dt square plus qt dx dt plus rtx equal to 0. If both the functions qt by pt and rt by pt are analytic at the point t equal to t0, then the point t equal to t0 is called the ordinary point of the differential equation, and we can apply the power series method to find the general solution of the differential equation given by equation number 12. As defined before, a point t equal to t0 is called a singular point of the differential equation 12 if any one or both the functions fails to be an analytic function. In the neighborhood of the singular point t0, solution of equation 12 becomes very large or oscillate very rapidly. Thus, solution of 12 may not be even continuous, and the method of power series solution will fail to work. Let us consider the differential equation t square x double dash plus 3t minus 1 into x dash plus x equal to 0. It can be easily shown that t equal to 0 is a singular point of equation 13. We will check here whether the power series solution work or not. Let us consider the solution of the given differential equation 13 to be of the form x t is equal to summation n equal to 0 to infinity a n t to the power n. Differentiating 14 twice, we will get x dash is equal to summation n equal to 0 to infinity n a n t to the power n minus 1, and x double dash is equal to summation n equal to 0 to infinity n into n minus 1 a n t to the power n minus 2. We substitute the values of x, x dash and x double dash in 13, and we will get t square summation n equal to 0 to infinity n into n minus 1 a n t to the power n minus 2 plus 3t minus 1 summation n equal to 0 to infinity n into a n t to the power n minus 1 plus summation n equal to 0 to infinity a n t to the power n equal to 0. If we simplify this, we will arrive to the expression summation n equal to 0 to infinity n square plus 2n plus 1 into a n t to the power n minus summation n equal to 0 to infinity n a n t to the power n minus 1 equal to 0. And as you can see, this particular expression is n plus 1 whole square, and hence we get equation 15, that is summation n equal to 0 to infinity n plus 1 whole square a n t to the power n minus summation n equal to 0 to infinity n a n t to the power n minus 1 equal to 0. We next equate coefficient of t to the power n from both sides of 15, and we get the first one is where we equate coefficient of t to the power 0, and we get a0 minus a1 equal to 0. In the second case, we equate coefficient of t to the power 1 from both sides, and we get 2 square a1 minus 2 a2 equal to 0, which implies a2 is equal to 2 a0. In the third case, we equate the coefficient of t square, and we get 3 square a2 minus 3 a3 equal to 0, which implies a3 which is equal to 3 a2, which can be replaced by 6 a1 and which is 3 factorial into a0, because a1 is equal to a0. In general, equating the coefficient of t to the power n, we will get n plus 1 whole square a n minus n plus 1 a n plus 1 equal to 0, which implies a n plus 1 equal to n plus 1 into a n, which is equal to n plus 1 factorial a 0. Thus, the solution will take of the form x equal to summation n equal to 0 to infinity n factorial a 0 t to the power n, which is equal to a 0 summation n equal to 0 to infinity n factorial t to the power n. To find the radius of convergence of the solution, we will have 1 by r is equal to limit n tends to infinity n plus 1 factorial divided by n factorial, which is infinite. Thus, we have the radius of convergence r equal to 0, which implies that the obtained solution is valid only at t equal to 0, and hence it is meaningless. The above example indicates that we cannot apply the power series method to solve a differential equation near a singular point. Our goal is to find a class of singular equations which we can solve near t equal to 0. So, we start with a very simple differential equation known as the Euler equation, which is singular, but we can easily solve near the singular point. Hence, we consider the example 4, where we have to solve the differential equation t square d2x dt square plus alpha t into dx dt plus beta x equal to 0, where alpha beta are constants, and this equation is known as the Euler-Cauchy equation. We can easily solve the above equation by changing the independent variable t given by s equal to e to the power t, and the equation 17 will be reduced to a new equivalent differential equation with constant coefficients and can be easily solved. Here we try to solve this Euler-Cauchy equation given by equation 17 without changing the independent variable. We will assume at first, for simplicity, that t is greater than 0, and let us observe that the coefficients are polynomial, and if we assume that solution is also a polynomial, say x equal to t to the power r, then t square x double dash and t x dash are both multiples of t to the power r. This suggests that we may try x equal to t to the power r as a solution of 17. We compute d dt of t to the power r and d 2t dt square of t to the power r, and we get r into t to the power r minus 1 and r into r minus 1 t to the power r minus 2. And next we have, after substituting these values, r into r minus 1 t to the power r plus alpha r t to the power r plus beta t to the power r. If we simplify, we will get this to be r into r minus 1 plus alpha r plus beta multiplied by t to the power r, which we represent as some function f r into t to the power r, where f r equal to r into r minus 1 plus alpha r plus beta, which is equal to r square plus alpha minus 1 into r plus beta. Hence, x equal to t to the power r is a solution of 17 if and only if r satisfies the following quadratic equation known as the indicial equation, given by r square plus r minus 1 into r plus beta equal to 0, given by 19. The solutions of 19 are given by r 1 equal to minus half into alpha minus 1 plus square root of alpha minus 1 whole square minus 4 beta, and r 2 equal to minus half multiplied by alpha minus 1 minus square root of alpha minus 1 square minus 4 beta. Now, we consider three cases depending upon the quantity alpha minus 1 whole square minus 4 beta, whether it is positive, negative or 0. In case 1, we consider alpha minus 1 whole square minus 4 beta is a positive quantity. In this case, equation 19 has two real unequal roots, and thus equation 17 has two solutions of the form x 1 equal to t to the power r 1 and x 2 equal to t to the power r 2. Since r 1 is not equal to r 2, the functions t to the power r 1 and t to the power r 2 are linearly independent, and hence the general solution of 17 is given by x t is equal to c 1 t to the power r 1 plus c 2 t to the power r 2. In case 2, we consider alpha minus 1 whole square minus 4 beta is equal to 0. In this case, r 1 is equal to r 2 and which is equal to 1 minus alpha divided by 2, and we have only one solution x t equal to t to the power r 1 of 17. To find the second linearly independent solution, we may use the method of reduction of order. Here, we would like to discuss an alternating method to have second linearly independent solution x 2. Since the quadratic polynomial f r has two equal roots, that is f r is equal to r minus r 1 whole square, from 18 we will have L t to the power r is equal to r minus r 1 whole square t to the power r. Taking partial derivative with respect to r on both sides of equation 20, we will get del del r of L is equal to del del r of r minus r 1 whole square t to the power r, and which will give r minus r 1 whole square t to the power r log t plus 2 times r minus r 1 t to the power r. The right hand side of 21 will be 0 at r equal to r 1. Hence, L t to the power r 1 ln t is equal to 0. Please note, when we write ln t, it is nothing but log t to the base e. Now, this result implies that x 2 is equal to t to the power r 1 ln t, which satisfies equation 17, and the ratio x 1 t divided by x 2 t is not a constant value. Hence, we can take x 2 t as a second solution of 17. The general solution of 17 in the case of equal roots is therefore given by x t equal to c 1 plus c 2 ln t multiplied by t to the power r, where t is positive. In case 3, alpha minus 1 whole square minus 4 beta is less than 0. In this case, both the roots be of the form r 1 equal to lambda plus I mu and r 2 equal to lambda minus I mu, with lambda equal to 1 minus alpha by 2 and mu equal to 4 beta minus alpha minus 1 whole square root of that divided by 2, and both are unequal complex roots. Hence, phi t is equal to t to the power lambda plus I mu, which can be written as t to the power lambda into t to the power I mu, which can be written as t to the power lambda into e to the power ln t whole to the power I mu, and if we simplify, we will get that is equal to t to the power lambda cos mu log t plus I sin mu log t, and it is a complex valued solution of 17. If we take x 1 equal to real part of phi t, which is equal to t to the power lambda cos mu log t, and x 2 equal to imaginary part of phi t, which is t to the power lambda sin of mu log t, they are the two real valued independent solution of 17. Hence, in the case of complex roots, the general solution of 17 is given by x t equal to t to the power lambda c1 cos mu ln t plus c2 sin mu ln t, where lambda and mu are given by 22. Now, when t is less than 0, we change the independent variable t by a new independent variable s, which is equal to minus t, and since t is less than 0, we will have s positive. And if we calculate the derivatives, dx ds is equal to minus dx dt and d2x ds square is equal to d2x dt square, and we can rewrite the equation 17 as s square d2x ds square plus alpha s dx ds plus beta x equal to 0, where s is positive. Since s is a dummy variable, so renaming s as t, we get the same equation as 17, and without the loss of generality, for mod t greater than 0, expressions of the general solution of 17 are given by, for case 1, where alpha minus 1 whole square minus 4 beta is greater than 0, x t is given by c1 mod t to the power r1 plus c2 mod t to the power r2, where mod t is positive. Case 2, alpha minus 1 square minus 4 beta equal to 0 is given by x t is equal to c1 plus c2 ln mod t into mod t whole to the power r. In case 3, alpha minus 1 whole square minus 4 beta is less than 0, and the solution is x t equal to t to the power lambda c1 cos mu log t plus c2 sin mu log mod t, where mod t is greater than 0, with lambda and mu is given by equation 22. In this module, we have learned how to find the ordinary and singular points of the second order differential equation. We have also seen what difficulty we face when we try to find the solution about the singular points and how to overcome it. In our next module 5, we will learn how to find the solution of the second order differential equation about the singular point using Frobenius method. Thank you.